Hi everyone, my name is Tovio Roberts. This is another Galvanize Data Science Prep Study Hall. I'm going to kind of continue from where I left off yesterday, but first I'm going to do a bit of review. So we wrote the Poisson Pmf, and I'm just going to go down here and outline writing the Poisson Pmf, and I'm just going to write it again. So I'll go ahead and delete it where it is, and we'll go ahead and do this again. So if we look at the PMF for Poisson, and by PMF I mean probability mass function, this is the kind of thing where if we have a Poisson type of problem, we're looking for the probability that k events occurs in some time period, okay? Now, what we know is lambda, right? This is the expected or average number of events for that time period. K is the number of events that we're looking for the probability of, right? This is a fairly simple formula, right? Lambda to the k multiplied by e, which is Euler's number, to the negative lambda over k factorial. Now, offhand, we need factorial, right? We need some kind of factorial function. Well, not some kind of, we need a factorial function. That's really easy to write. The factorial of some number n, or, some number. This is just going to be the product, which will begin at 1, and we'll say for n in range, and we'll just go from 1 up to the number and include it, so number plus 1. We'll just say product times gets that value n, and we can return the product. So that takes care of the factorial portion. If we want to write the Poisson Pmf, which we do, so let's write Poisson Pmf, and that's going to be for some value of k. The way this looks, it's as simple. This is a simple mathematical form. We can just return lambda. If I'm just translating this directly, lambda. Sorry, I need lambda in here too. That's our expected value. That's our expected number of events, our average number of events. However you might see that written. This is to the k, and that's going to be multiplied by e. All right, which we need to import. This is e to the negative lambda, and this is all divided by factorial of k. So to get e in here, we can just say from math import e, and that'll work. Okay, so there are a couple problems down here that I think I showed yesterday. You're reading a book, you see the word the appear 20 times every 5 minutes on average when reading. What is the probability that you will see the appear 30 times in the next 7 minutes? Okay. Lambda in this case is going to be, well, if it's 20 times for every 5 minutes, then it's going to be 20 times 7 over 5 for 7 minutes, right? 7 minutes divided by 5 minutes. That gives us a growth factor. We then multiply that by 20. And we're looking for k of 30, and we can just plug that in. Poisson Pmf lambda gets that lambda, k gets that k, and we get a result. So that's an example of a Poisson problem that uses the PMF. And then here's a problem that uses the CDF. What is the probability that you will see the word the appear more than 30 times in the next 7 minutes? Okay, well, this is just going to be lambda. That's that same lambda, right? 20 times 7 over 5. And we're talking more than 30 times. So first, we're going to calculate the probability of seeing the 30 or less times. That's why I've got this LTE, less than or equal to 30. And I'm starting that at 0, and we're going to accumulate the PMF for every value from 0 up until 30 plus 1 right here into this LTE 30. And then we can just take the complement of that in order to answer the question more than 30 times. So this is a CDF, right? So maybe I'll just code this out really quick as well. I'll just translate this into a reusable function. So def Poisson Cdf, and there's going to be a lambda and a k. I'm going to call this k high, just for purposes here. And I'm going to say for well, we can still have an accumulator, right? In this case, I called it product, but here maybe I'll just call it accumulator. And I'll start it at 0. And I'm going to say for, I'm just going to snag this little bit of code. And I'm going to say for k in range, I'm going to start at 0, and I'm going to go to k high plus 1. K high plus 1. And this accumulator is going to get the Poisson Pmf for those values, and then we can just return the accumulator. So that's a way that we can do that. Let's see. Let me just scroll down here. What do we have in the Poisson lesson? So that is a translation of this CDF, right? So whenever you see something like this, if you're not familiar with this notation, this is sigma for sigma or summation, and we're going from a value of 0 up until k, inclusive of k, and we're summing all the results of this, and that's exactly what we're doing in code over here. So we've created a direct translation of the CDF in this function. So we've got our lambda and all this here. Instead of this little bit of code, we can say 1 minus. We can say 1 minus the Poisson Cdf lambda, and then less than or equal to 30, and that will work exactly as we would expect it. Okay. All right. So now we've got this Poisson Pmf, we've got this Poisson Cdf, and I'm gonna just erase these problems in here really quick. And maybe clean up my code just a little bit. Okay. So we've got factorial. Poisson Pmf is dependent on factorial. Poisson Cdf is dependent on Poisson Pmf. And so these are all calling out to each other. So what can we do with this? Well, there's a number of things we could do. And I'm just going to show a quick and easy thing that we can do to analyze the distribution that the Poisson Pmf is showing. The Poisson distribution. We can look at this through the lens of a dictionary. So I'll write this first just in Python, and then I'll code it out in. I'll just abstract it out to its own function. So we've got this dictionary. And we can say for k in range, and we'll go from 0 to, let's say, 30. And I'm going to say d sub k. Oops, sub k. This is just going to get the Poisson Pmf. And maybe I'll call this d Pmf. It's going to get the Poisson Pmf of some lambda and k. So maybe I'll also set a lambda here. I'll set a lambda of 10. And then we can just say for k v in d Pmf dot items, I'm going to print the key and the value. And this is going to show us all the values, all the probabilities of k between when there's a lambda of 10 for k values between 0 and 30. Okay, so let's take a look at this. If we have a lambda of 10, we would expect our highest values, our highest probabilities, to be right here, right at right around 9 and 10, and that's what we see, right? 0.125 is the highest probability that we're seeing. Now, you can see that we've got tails going down on the ends, and we get something sort of bell-shaped, but we have some skew out to the right because this goes out to infinity, right? The right side of the Poisson distribution goes out to infinity, and we just get increasingly lower and lower values, probability values. Okay, so that's using the Poisson Pmf. And if I want to put this into a dictionary, if I want to put this into a function, I can call this Poisson, I'll just call it Poisson Dictionary. We need a lambda value, and maybe I'll default that to 10, right? So that gets rid of that. We also want a low k, and we want a high k. And actually, I'm not going to default that to 10. I'm just going to leave it blank. And we're going to say for k in range, low k to high k plus 1. We're going to pack in this dictionary, and we can just return it like so. So it's a good skill to be able to just take, take some code and turn it into a function, right? Abstract it out into a function, and that makes it reusable. So I'm going to take this. And let's say we want to go, we want a lambda of 10, we want a low k of 0, and a high k of 30. This should do the exact same thing as what we just saw, and it does. All right, so I called this Poisson Dict, but let me call this Poisson Pmf Dict. I think that's a better name. And then, there's a statement here. I was reading last night that the Poisson distribution is, in theory, a derivation of the binomial distribution. Any chance you could explain that briefly? Yeah. So I used to do this explanation. Let me think about this. Let me think about a Poisson problem and try to start approaching this in a binomial way. I used to do this, I used to explain it this way all the time. Let's just see. Let me see where I end up with this. All right, so we'll make a problem. We'll say a busy mall has, on average, 6 people walk through the front door every minute. And this should clue you off to being something like a Poisson distribution, just by, on average, some number does something in some span of time or volume of space, something like that. So we might ask the question, what is the probability that I don't know, 10 people walk through the front door in 2 minutes? Okay, well, we can approach this with Poisson. We can say there's a lambda of, lambda is 6 for for 1 minute, lambda is 12. So let's call this lambda 1, call this lambda 2. Lambda is 12 for 2 minutes, right? So that's something we can see. If we're trying to consider this probability, we might think, well, in 1 minute, we might break this down into some more basic form. So in 1 minute, 6 people, on average, walk through a door. In 30 seconds, 3 people, on average, walk through a door. In 10 seconds, 1 person, on average, walks through a door. So if we think of every 10 seconds as being a single trial, then it's kind of a Bernoulli trial, right? Like, 1 second is 1 Bernoulli trial. So 1 second. Sorry, 10 seconds. And then at 20 seconds, right? If I make a timeline. And then 30 seconds and 40 seconds and so on. And so we might look at this and say, okay, well, in 10 seconds, we're either going to have a 0 or a 1, right? It's either a failure or a success. I'll do F or S. And that same thing is going to be true for each of these, right? So what is the probability that there's a failure or a success in those 10 seconds? Well, in our current idea of this, it might be 0.5, right? We're either going to get somebody or we're not, and it feels a little bit like a coin flip. Now, this is not equivalent to Poisson. Just to be honest, it's not. So if we're considering failure or success for 1 minute, and we're considering every 10 seconds as a sort of box, as a single trial for failure or success, then we can kind of break this down into, well, what are all the possibilities in 60 seconds, right? It's we can say failure, 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 failure. Okay. We could say failure, 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 success, right? And this starts looking like binary. I mean, it is binary. And I could sit here and continue counting, but I think you get the idea. So now, this is not equivalent to Poisson, but we want to consider it in this way as like a kind of naive way to approach it, right? There are a lot of reasons why this is not equivalent to Poisson, because initially we're saying on average 6 people walk through a door every minute, and so this is more representative of our expectation, this all ones. But if we're going to break this down toward binomial, then we need some sort of discretized trial, and that could be in the minutes, right? Now, another problem with this, using binomial in this approach, is that we could get all of these people through the door in 10 seconds. So we could have, let's say, in 10 seconds, 6 people walk through, right, if this is our expectation. So 6 people pass, and then 0 pass in the remaining 50 seconds, right? So even though there is a naive approach that we can take here, notice that this is going to get us a probability that's not not really in the realm of what we're looking for, right? Now, there is a longer derivation that I've been thinking about just making a derivation video for this. Not really a derivation so much as a light derivation with a lot of explanation about how we get from binomial to Poisson. I'm not going to do that right now because I'd like to prepare it and actually make it like something that I post in the materials and that we embed for people who want a further explanation. But you can, like, it's strange, but you can use something like a binomial process to give you a naive probability for a Poisson event. But Poisson is just so convenient that we're going to use Poisson for these in general. That said, yeah, you can discretize moments, right? Like in 10 seconds, one person on average walks through a door. You're either going to have a person walk through or you're not. So there is a sort of intuition there about how we can get from binomial to Poisson. Yeah, I'll make a note. I've been meaning to make this derivations video for a bit because I think it's interesting. It's fun. Yeah. So hopefully that's helpful in, in some way to build some intuition about how we might end up at Poisson. But I'll put together a derivations video and yeah, maybe I'll try to do that tomorrow. Yeah, because we'd have to lightly derive Euler's number as well, and there's a few different ways to do that. And yeah, Euler's number is a fun derivation actually, or fun. Derivation's the wrong word. I don't mean to use that word improperly. Like arriving at Euler's number is pretty fun. There's a really great channel that I don't know how many of you watch this channel, but I love it. And there are a number of times that I'll be watching something on this and I'll pause it and I'll just start coding out the idea and create some code to prove to myself the things that they're saying. And that's just I don't know, it's a fun thing to do. That's actually where I ended up with, there's a video I made on, let's see, number file, I think it's, yeah, the coronavirus curve. I watched this and then I coded out an SIR model, which is what he's talking about here. Just a model of disease transfer. Sorry, I'm getting a little on a tangent here, but I think if I remember right, yeah, this video, Euler's number. I think I remember this video being really good. Sorry, let me just grab this link. If you're interested in watching this, I'll just throw it in the Slack. Anyway, yeah, because we'd have to walk through Euler's number, and then I think in the same video I'd want to like give a binomial basis for geometric because that's really straightforward, right? But giving a binomial basis for Poisson is a little bit weirder, but it's fun. Okay, so I think we were just talking about. Oh yeah, we were talking about the Poisson Pmf Dictionary. And simple enough function here, Poisson Pmf Dictionary. Now, if we want to make a Poisson Cdf Dictionary, it's also relatively simple, and it's just a little bit of different code here. So there's a couple ways I could do this. I could say for k in range, low k to high k, I've got this d sub Pmf of k is going to get the Poisson Pmf. I could instead get a proba and then I could also throw an accumulator in here, and I could say accumulator plus gets the probability, and then I can just do this, right? And suddenly I have a CDF function instead. So, you know, same thing. I've got this dictionary. I'm getting the probability. I'm tacking the probability onto the accumulator. So oh, I should probably call this dCDF. Change that. So this would be one way to do this, right? Where I've got this running accumulator. I've also got a Poisson Cdf CDF function up here, I think. Yep. I've got a Poisson Cdf function that instead of doing this way, this works, or this should work. You know what? Let me go ahead and run it, make sure. And I'll just grab all of this. And I'll change this to CDF. And notice, this should make sense, right? We're starting with make this a little bit bigger. We're starting with a very low number, and this number can only increase, and we start heading toward 1, right? So we're getting very close to 1 even when we're out at 30. Of course, we're never going to get to 1 because this skews out into infinity. So that's one way we could write this. The other way we could write it, maybe this is obvious, but we could just call the Poisson CDF on lambda and k, and that would work in the exact same way. So either way works. This is a little bit less code, and you wouldn't need the accumulator in this form. So that's thinking about the CDF just briefly. But let's go back to thinking about the PMF and this PMF dictionary. If you're thinking about how many items, how many occurrences of K you would expect to see in a Poisson-like phenomenon. Like, let's say you have, let me think of a story problem on this. You have a space telescope. Let's say it's just floating out in space. You happen to be very rich, and you have a space telescope. This telescope takes, let's say, 1,000 images a day. On average, each image has, let's keep this number kind of low, has 20 fully discernible, well, what do I even mean by that? 20 stars where, let's say 20 stars with a luminance, let's say let's say with luminance values that are sufficient to gain certain important readings, important measurements. How about that? So that's on average. This is a kind of classic Poisson idea, right? There's 20 stars on average, but you might have images that have no stars, and you might have images that have hundreds of stars, and we're taking 1,000 images a day. So on any given day, you're building a Poisson distribution you're building. You might take these measurements and you might notate the number of stars visible on each image, and then you might count your k values, right? Your actual observed k values. And if you do this every day, and then you average this across all your days, like let's say over 1,000 days. So let's say you do this every day for 1,000 days. What would be your average number of, let's see, your average count of images for each count of stars from 0 to 30. Let's say 0 to 40. Okay. So we've got a lambda, 20 stars. Let's think about how to answer this question. It's kind of a tricky question to ask, but it's going to be pretty easy to answer this, actually. So the first thing that we might answer is, well, what is the probability of, for each count of stars was the estimated probability, well, let me leave estimated out of that. I'm going to use that later. What is the probability for each count of stars across a day's images? Okay, well, we can answer that. We've got this Poisson Pmf Dictionary function. And so I'm just going to snag this. And I'll call this daily stars probabilities. And our lambda is 20. And we're thinking about counts of stars between 0 and 40. And we're just going to assume everything else is outliers, right? So I'm just going to say for key value in daily stars probas dot items, and let's see what that gets us. Okay. So 20. It turns out that 20 is our highest probability, right? And 2019, right? And that's normal. That's what we would expect, given our expectation of 20 stars, or our average of 20 stars across images for any given day. So, you know, that doesn't mean that we've actually observed this. It just means that these are the probabilities that we would expect. We would expect something like this, right? If we were to sample for 1,000 days or 10,000 days or something like that, and build these probabilities as we go, right? So we can first answer that question, but then we can answer this next question pretty easily with this understanding, right? All we really have to do here is multiply v times 1,000. And this is going to get us an expected number of stars, you know, let's say averaged across all these different sets of observations. So I might just round this. And why am I getting an error there? Oh, that's why. Okay. So we might see 89 images that have 20 stars. and we might see 39 images. This is what our expectation would be, that 39 of the images would have 14 stars, and 18 of the images would have 28, and that no images would have 0 stars, no images would have 4. So it doesn't mean that in a given day's observation we don't have an image with 0 stars, we don't have an image with 40 stars. It just means that averaged over all of those, this is what we would expect to see, right? Where 89 stars, sorry, 20 stars occurs 89 times in 1,000 images. That's what we would expect. It doesn't mean that that's what would happen on any given day, right? It just means that that's what we're going to expect in general. Okay. So that's kind of a lot about Poisson. I might just copy paste this into the Slack. And let's see what other kind of stuff we have in here. Okay, cool. So let's kind of back up and let's consider Bernoulli. So we call this Bernoulli Distribution. I honestly have always called it a Bernoulli Trial. And my reasoning there is that, you know, I guess we could call it a distribution, but there's only one of two outcomes, right? We're either going to have a failure or a success. And it's not really that we have a whole string of trials, it's just a single trial. So this is a single coin flip, for instance, or an unfair coin flip, or however we want to consider that. So how might we code that? Well, let's think about that. If we want to make this agnostic of the probability, if we want to be able to put in any probability, then we're going to have to do something. We're going to have to do something a little bit more complex than what I'm going to do right now. But if we just want a simple Bernoulli trial with a probability of 0.5, we could just do something like this. Simple Bernoulli. It won't take any argument. And I'm going to say from random import choice. And we're just going to return the choice from 0 or 1, right? So if I print this, this is just going to get us a 0 or a 1. And it does, right? What might be a little more helpful is a Bernoulli trial where we can change the probability, right? This has a static probability of 0.5. And that's not really very practical for a single Bernoulli trial. So let's write something a little more helpful. And we're going to say Bernoulli, well, we want to put in a probability of success, right? And I'm going to default that to 0.5. That's fine. And I'm going to say, well, I'm going to need something else here. I'm going to need another function from random. So I'm going to say from random import choice, but also import random. And I'm going to say, well, a single draw is going to get a number between 0 and 1 from random. And let me just print that draw. Oh, I should probably actually call this function. All right. So notice this is going to get us a random number between 0 and 1. This is a uniform distribution. It's going to get us any number between 0 and 1. So that's good. That's what we want. all I need to do to get a Bernoulli outcome from this, either a failure or a success, I can say if the draw is less than the probability of success, then we're successful, right? And we can say true. We can return true. And otherwise, we can return false. And so now if I run this, we should see true or false half the time. If I print this, we should be able to see that. So true, false, 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 lots of falses. My suspicion is that this is going to even out, and why don't I just qualify that suspicion and write something really quick to do that. Let's say we're going to do this a number of trials, and let's do it 100,000 times. And I'm going to say the number of successes. We're just going to make a little accumulator here for the number of successes, and I'm going to say the probability of success is 0.23, and I'm going to do this for whatever in range num trials times, and I'll say if Bernoulli, right, with the probability of success, if that is true, I could say is true. If that's true, I don't need to. I can just say that's going to evaluate to true or false either way. Then I can say the number of trials that are successful is going to get incremented by 1. And then let's just print the trials success divided by the number of trials, right? So let's see how close we get to 0.23 with that. We get pretty close, right? 0.23175. Now, we're not going to always get 0.23, but we're going to get it a lot of the time, right? So when you're writing code, when you're exploring statistical concepts, kind of you want to write something that verifies to you that it's doing what you think it's doing. That's pretty important, and this uses a random process in order to make that verification, right? And it verifies it pretty well, right? We're seeing 0.23, which is essentially, well, that is what I wanted to set for my probability of success. Now I could make this more granular, 0.23574, and we can try that again, and we can see how well it does. 0.236, 0.235, 0.236, right? It's getting close, I'm not getting exactly 0.23574. Maybe I'll get a little bit better if I do more trials, right? And this should be sort of intuitive. The more trials you do, the more confidence you have, right? We're just testing this again and again and again. So I'll do some more trials. Takes a little bit long, just slightly longer to run, not much longer. But now we get 0.23572. We're not getting 0.23574, but that's okay. We're at least covering the 0.235 pretty regularly. So that's cool. This is going to take a little bit longer, but let's do 10 million trials and just see. And there it is, 0.2358. Okay. We're probably going to get a 7.4 in there before too long, but I think we've already proven to ourselves that this scheme works okay, right? I'll just bring this back to 100,000, and I think it's fine for our purposes here. So that's a simple Bernoulli trial, right? And when we're thinking about Bernoulli trials, we're really just thinking about this, right? The probability of success, probability of failure. Probability of failure is obviously 1 minus the probability of success. Expected value, it's just the probability, as it turns out. The probability times, p times 1 minus p, right? Probability times 1 minus the probability. And so, we've got these visualizations here. A lot of these feel a little bit, what's the word? Like a little bit like tautologies, right? If we're plotting, Bernoulli trials with a probability of 9, well, that's 0.1 of the time failure is going to happen, 0.9 of the time success is going to happen, and it's really not so complex, right? It's pretty straightforward. And I'm just seeing if there's anything else in here that is relevant or that I haven't talked about. Okay, so from Bernoulli, we can start getting an idea of the binomial distribution. And binomial distribution, we want you to be fairly comfortable with it for the technical interview. We want you to at least be able to notice something like this. Binary can represent a series of Bernoulli trials, right? So failure, right? Here, let's say failure, success, success, failure. That's a randomly generated series of binary, right? And we can think about this as a series of trials, of independent trials. What is the probability of this specific outcome? Well, if it's binary and we're randomly selecting zeros and ones, it's 0.5 to the, what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9 to the 9th power that we're going to get this specific outcome. With binomial, though, if we want to take this a step further, we might ask the question, in binomial, we might ask the question, what is the probability of getting 4 ones in let me comment that out, in a length, let's call this length 9, let's say 9-bit randomly generated binary word. We sometimes call these words. Instead of binary numbers, we sometimes call them binary words. We'll tend to refer to them as binary numbers, but either way is fine. So this is not, the answer to this is not just 0.5 to the 9th power. This is, in this case, maybe I'll extend this question. What we're really asking here is, what is the probability of getting this exact binary word if you are generating binary at a probability of 0.5. Generating bits at a probability of 0.5 to get a 1 value. Sorry, it's a little bit wordy, but it's just this, right? It's 0.5 to the 9th power in that case. Binomial is different because, well, if we're considering 4 bits in 4 ones in 9-bit binary, well, we've got a few different ways that we can represent this. 1, 2, 3, 4, 5, 6, 7, 8, 9. These last 4 are ones, right? We could also do this, right? We could also do that. We could also do that. And we could do a lot more. Sorry, not that. That's not correct. That's correct. And then there are so many more. So notice these are different arrangements. These are different arrangements of ones across ones and zeros across 9 trials. they're all different arrangements of failures and successes across 9 trials. So it's not as easy as just this simple, well, each trial is independent and we can just get the probability by multiplying them all together, 0.5 times 0.5 times 0.5 9 times. We need some way to build this out and, sort of systematically answer this question. One way we could do this, and I don't necessarily recommend this, but I'll show you this. This is one of those things where I think maybe it'll be computationally intractable and take a little bit long, or take a little bit too long. But let's try it. I could do this. I could build the entire sample space. So let's say there's sample space, and I'm just going to make a count of the sample space, and I'll call this the 4's subspace. And I could build this using this kind of nested for loop approach. There are other ways I could do this that would be a little, which I'll do. I'll go ahead and do. I think I've done this before in one of our study halls, but since no one's asking questions at the moment, I think maybe I'll explore this concept. So we could do a bunch of nested for loops, and this is going to get us a bunch of binary. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Not sure if this is going to run, but we'll find out. It might be a little bit too much binary. L, M, N, O, P, and Q. And I'll just point out right now that our sample space is actually going to be 2 to the 9th power. And that's what we're going to get here with the scheme that I'm using to build this. So, let's say binary. Let's just call this binary. It's going to be an empty list, and maybe what I'll do is, you know what? I don't need to do that. I'm just going to count in a list. I'm going to say, I'll call this bin count. It's going to be a list from I, J, K, L, M, N, O, P, Q. Right? That's 8. Yep. And then I'm going to say, if bin count dot count of 1 is 4, right? Because we're looking for all the arrangements of 4 across this. If that's 4, then let's go ahead and increment the 4's subspace by 1. But in all conditions, in all circumstances, we want to increment the sample space by 1. We could just do this initially and not do this incrementation. We could just say 2 to the 9th, but I'm just trying to do this in the most terrible brute force way possible in order to answer this question. And if we want this probability, we can just say, well, the 4's subspace divided by the sample space. So let's get this running, and then let's do something that's not quite this brute force. Oh, really? Wait a minute. I don't trust it. Why did that run so fast? The thing is, I think that's correct. I was really expecting this to take a really long time to run because I'm constantly trying to show these terrible nested for loop brute force approaches to building sample spaces and building subspaces. But yeah, let's verify this. Let's let's go ahead and take a different approach. So we've got the binomial distribution. We've got this probability mass function for the binomial distribution. So let's grab that. And notice here we've got this combinations function. Let me grab the formula for combinations because I'm going to code that as well. That's under basic probability. Combinations, yeah. And that's permutations. I actually want combinations. So there's combinations. I'll go back to discrete probability distributions and binomial distribution, and we'll stay there. All right. So if we want to create the kind of an equivalent idea here, we'll probably want to compare this to the result here, this 0.24. We'll probably want to compare that to the results of the binomial PMF, right? So let's do that. We'll start from the beginning with this. We'll just code combinations, and the first thing we need for that is our good old factorial, which I'll code again and again and again and again. So factorial of some number is, well, I've already done this once today, so I'll just write it really quick. For n in range, go 1 to num plus 1, and prod times gets n and return the products. And let's just test that. So factorial of 5 should be 120. And it is. Okay. So the next thing, because we've got combinations in here, right there, we're going to need that combinations formula. So that's an easy function to write. It's just here. I'm just going to call this comb and n choose k. I usually use k. It's showing r here, but that doesn't really matter. We can just return factorial. K and r are the same thing. It just depends on, who taught you statistics and probability. So factorial of factorial of n divided by, this is n minus k factorial multiplied by k factorial. Okay. And that's just going to give us, it's going to give us the combinations of n choose k. Okay, so we've got that part. Go ahead and get rid of that. Now we can just write the binomial PMF. So def binomial PMF, and this is just going to be n, k, and some probability. And for the probability, I'm just going to default that to 0.5. And we can simply return the combinations of n choose k, right? N and k, which is that first part. So we've got that. And we can multiply by p raised to the k, k. And that's going to be multiplied by 1 minus p raised to the n minus k. Okay. Oops. I think I call that com. Let's call it combs. Okay. So we've got that. And what was our original question? It was 4 successes in 9 trials with a probability of 0.5. So let's see if that gets us the same answer. And it should, unless there's something wrong in my code. So we've got 9 trials, k of 4. And I'll uncomment this up here as well. So that's uncanny, right? That's two different routes to the same answer. And we don't even see any sort of precision loss here. We get the exact same answer. So that's cool. That's heartening. I don't think, I don't think that one way is more correct than the other. But to be honest, this is only going to last you so long. This massive wall of for loops, of nested for loops. That's not gonna be great for you in the long run. This approach, this is sort of you've got these closed form. You've got this closed form binomial PMF, and you can answer the question. Out of 9 trials, what is the probability of getting 4 successes? If the probability of success of a single trial is 0.5, well, you can just plug that into a binomial PMF and you'll get an answer there. So I'm going to comment out this big, massive wall, this terrible thing that I did. And we're going to continue with some of these ideas. So, we've got the binomial PMF. The binomial CDF is something that we can just pretty easily code out. So why don't I do that? I'm going to say, well, the binomial CDF, we're going to take n and then a high value of k high, I'll call it, and a probability, of course, and I'll default that to 0.5. And we can just do this with this same accumulator kind of idea. We'll start the accumulator at 0. It makes more sense to start it at 0.0. Doesn't really matter though, okay? So 0.0, and I'm gonna say for k in range k high, and we want to include k high, right? This is cumulative. We're asking questions like, what is the probability that you're going to get 4 or less successes in 9 trials? So we want to include k high. And I'm just going to say this accumulator is going to be incremented by the binomial PMF of n, k, and p, right? So n, the current k, and of course the probability. And then we can just return the accumulator. So we might ask the question, what is the probability of getting 4 or less successes in 9 trials? That's easy to answer with the CDF. We can say that's just the binomial CDF. Oop, I thought that I'd be able to use code completion, but apparently not. That's the binomial CDF of 9, 4, and with a probability of 0.5. And so we should be able to see that. It's 0.5. So let's think of 3 or less successes, just really quick. So 3 or less successes is going to be 0.253. All right. So I think that's pretty easy, pretty straightforward. As before, we can build a binomial dictionary, right? We can say we can build a binomial PMF dictionary. Why don't we do that? Def binomial PMF dictionary, and we're going to have an n value, a k low this time, k high, and of course a probability. Okay. And from that, we can just build a dictionary. This is the same thing, same pattern that we really want you to know this pattern. This using a dictionary to explore things. I'm going to say for k in range k low to k high plus 1. And I'm going to say d sub k. This is going to get the binomial PMF, n, k, and p. And then we can just return the dictionary. And this is going to be that same printing pattern, right, where for key value in, and I'm just going to call this directly with a few values. I'm going to say an n of 9, k low of 0, and k high of 9 with a probability of 0.5, and then dot items. I'll just print an f string of the key and the value, right? Okay, so let's see what that gets us. We should expect oh, interesting. Oh yeah. Well, that totally makes sense. The CDF of 4 was 0.5. Yeah, and so, you know, looking at this, we can take a look at the probabilities for all these different values of k, and I think that's kind of convenient, right? You know, we were focused on 4. That was where we were originally focused. And of course, that's the same value that we were getting up here that we verified through the binomial process that we wrote. Yeah, pretty straightforward, pretty easy. So that's a Binomial Pmf Dictionary. How do we write the Binomial Cdf Dictionary? That's easy enough. Let's just write that. So same kind of idea. I have some accumulator started at 0.0, and instead of this happening like that, I'm going to take this and put it into a probability, and I'm going to say the accumulator is going to be incremented by the probability, and the d sub k is going to get the accumulator, and then I'll just take this printing pattern that I have, and I'll use that. And so now we can take a look at the Binomial CDF Dictionary for the same values. This is where we saw that 4 trials out of 9, 4 successes out of 9 trials with a probability of 0.5. Well, the probability of that is 0.5, which, you know, you think about it and it makes sense. And so notice this is starting low and it's going up, and it's doing something like that, right? So within 9 trials, of course, you know, the probability of getting 9 or less successes in 9 trials is going to be 1, right? Because you might get 0 successes. So that makes sense. Cool. Let me think about, yeah. So that's a lot of what we talk about here in this binomial distribution. Let me see what the other thing we have. Binomial distribution with Python. That's kind of all I'm doing is the binomial distribution with Python. I'm doing it a little bit differently from what we see here, but that's to kind of give multiple angles on the same type of problem. So let's take another angle on this. I think this is this gets interesting. I think this is going to help us kind of understand a generalized sampling approach. That's really kind of the idea. So I'm going to, I'll just say, I don't know, I'll say sampling approach. We've kind of taken a counting approach. We've taken an approach using the PMF. But now let's build some samples. So I'm going to do this by saying from random import choice. And I'm going to stick with this 0.5 probability because I think it illustrates well and I can keep it simple. So I'm going to generate some binary, and I'll call this generate n bits, and n I'll default it to 8. And I'll say, well, we've got some list. This is going to be a list of binary. I'm going to say for whatever in range n, and I'm going to list.append a choice out of the list 0 and 1, right? So let's return the list. This will give us some binary to work with. So let me print generate n bits, defaulted to 8. Okay, so that works, right? If I keep running this, I'm going to get some different number of bits as ones and as zeros, and that's just what we expect to see. Okay, so I'm going to create a sampling dictionary. I'll write a function called, how about binary sampling dictionary. And it has n bits, and let's say the number of samples is 1,000, not 10,000, but 1,000. And, you know, this will be a dictionary that I pack in. I'm going to say for whatever in range, and it's going to be the number of samples. Okay. So if we're thinking about binomial as a series of Bernoulli trials, then the number of successes is just the sum of the binary, right? So 0 plus 1 plus 1 plus 1 plus 1 plus 0 plus 0 plus 0 is just 4, right? We're counting the ones. So that's easy enough to do. I can say I'm going to make some binary, and I'll call out to generate n bits, and I'm going to do that num. I'm going to pass in the number of bits, and then I'm going to get the sum of those bits. Okay, the sum of the bits is going to be just the sum of the binary. That's easy. And then I'm going to see if that sum is already in the dictionary. So I'm going to say if the sum of the bits is not in the dictionary, then I'm going to say d sub sum of the bits. I'm going to initialize that to 0, and then I'm going to increment by 1. If you've watched me, this is usually how I do this. So plus gets 1, and then I'm going to return the dictionary. And so I don't have to type this over and over again. I'm just going to grab this for key value print statement, and let's take a look at this. So binary sampling dictionary, let me grab that. Maybe I'll default this to 8 so we don't have to have as much code. Okay, in whatever that returns, dot items. Okay, so let's see what that gives us. First, if sum of bits not in, that's what that should be, not in D. Okay. Num samples, num samples is not defined. Okay. Notice this is not in any given order because dictionaries don't guarantee order. So let me do that. And maybe I'll change this to 9 since we've been doing out of 9 in general. List object has no attribute items. Oh, that makes sense. Okay. All right. So here we've got some counts. And this is one round of sampling. This is one round of sampling. And as we'd expect, you know, 4 is our highest number here, and that's fine. If I run this again, of course, we're going to get different numbers. And that's okay, right? This is like one round of a random process. And we even get times where 5 is greater than 4, which makes sense as well because 5 and 4 have equal probability for successes. Okay, so there's a question. Why do I prime the dictionary with gets 0 and not gets 1? I could do gets 1, right? I could do that. But then I would have to do this. So else we do that. So it's just the way, it's the style that I do it in. It's not to say that one way is better than the other. This, I like the idea of this being a catch-all in some way, but it's not that it's better. So I just assume, you know, prime this with 0 and then increment every time with 1. But you know, it doesn't matter. You can do this either way. I'll leave it like this because I think sometimes this is less confusing to people. Okay. So so we've got that. Now, so let's take this a little further. Let's build these samples over and over again. So let's build these samples 1,000 times. And I'll just call this binary, I don't know, let's call it binary sampling, that's dictionary. How about we call it binary sampling trials dictionary? How about that? That seems okay. Again, the number of bits, which we're going to do 9. The number of samples we'll keep at 1,000. And then I'm going to say the number of trials we're also going to do 1,000. So this is, yeah, we'll just see what happens. Okay. I'm going to make another dictionary, right? This is what we're making, dictionaries. And I'm going to say for whatever in range the number of sample trials, the number of trials, I think is what I called that. And then I'm going to say, I'm going to build this dictionary of the binary sampling dictionary. And we're going to say number of bits and number of samples. And then for key value in d.items, I'll say if the key is not in d sub out, then d sub out sub key is going to get an empty list, and in every case d sub out. So I'm going to go back to my convention here. Just notice that it's the same thing. I could rewrite this in another way and it'll be fine. I'm going to append the value. Okay. So what this is going to get me is this is going to get me a dictionary with all of the values that from the original sampling dictionary. So let's just return that. I'm going to modify this a bit more. Return the dictionary. Yeah. I'm going to modify this a bit more in a minute because I actually want something else out of this. So, but let's take a look at it. It might be a little bit messy. So binary sampling dictionary, this is going to be the binary sampling trials dictionary. And we need number of trials now, number of trials. And let's try with 1,000. That might be too much. Binary sampling trials dictionary, number of bits. It's going to be 9. Number of sample. What am I missing here? Number of samples, number of trials. Oh, I see. I just had that doubled up. Okay. So let's try that. I think this is going to take a little bit of time to run. Oh, not that long, actually. Okay. And this is where we settled in... Oh, what's going on here? I've got something going on here. Oh, I'm returning the wrong thing. I'm returning D. I should be returning D out. That's all. Okay. Okay. That's going to be unreadable for really good reasons. Instead of doing v, I'm just going to do the first few values of v. I'll do up until 10 values. So hopefully that'll fit on a single line. There we go. And, you know, just keep in mind that this is going to go off to the right further than is showing here. But that's fine. Just do that one more time. Looking at this, we should be able to average all of these values and sort of converge on an expectation, or converge toward an expectation that looks more like the theoretical distribution for binomial. And so why don't we do that? I'll modify this again. Let's see. How do I want to do this? I'll do this, and I'll write yet another function, and I'll just say trials, binary sampling. How about, let's call this estimations dictionary, and we can call to the binary sampling trials dictionary. I know this is getting it's getting a little out of hand. So many functions that are all kind of doing the same thing, but we'll see. So I'll say D is going to get the binary sampling trials dictionary. I'll just pass in the number of bits, number of samples. You know, I can just do this, and number of trials. That just gets repeated, and then I'm going to say for k, v, and d.items. And I'm just going to modify d sub k to be the average number, right? That we're expecting to see, the average count we're expecting to see. So d sub k here is just going to be the sum of v divided by the length of v, right? That's just our mean of the v, and I can return that dictionary. So this looks a little bit like things I've been doing over the past few days, where we kind of converge. Let's say we converge on a mean. And I really wish I would have done converging on a variance, because I think that's really interesting too. But maybe I'll do that at a different time when we come back around. Okay, so num samples 1,000, num trials 1,000. We're dealing with length 9, and our v should now be our estimate, right? So this will probably take around the same amount of time as the prior function. And let's take a look at this. These are, let's say, our expected counts of these occurrences of k. And so that's kind of, that's kind of reassuring, right? 2.27 is very close to 2.31. We're seeing a bell shape here. And why don't we sort of rein this back into probabilities or something like, let's say, probability estimates. So I'm going to make one more of these, and it's going to look like this. Yeah, let's do it like that. So I'm going to do binary sampling. I'll say estimated probas dictionary. Same everything here, except I'm going to call out to. It's a little silly, but I'm going to go ahead and do it anyway. I'm going to call out to the most recent function that was written, and now we can just say that estimated count, those estimated counts are going to be divided by the number of samples. And that should get us, unless I'm misthinking anything here, that should get us a list of probabilities that looks something like the PMF that we did up here. So let me find that. Binomial Cdf Dict, okay. Binomial Pmf Dictionary, and for KV and Binomial Pmf Dictionary. So we're trying to make something that looks like this. That's sort of arriving closer to that. So let's see. Let's see how that turns out. Oh, I probably should put a couple line breaks in there just to make it a little more readable. There we go. And that's pretty good. Like, here, I'll blow these up a little bit because I'm sometimes surprised how I shouldn't be surprised that these turn out kind of pretty good. But let's take a look at this, because we're getting reasonably close, right? And you know, like, look at this in our estimation. Here's the probability of k equals 4, right? 0.2456, 0.246, right? This rounded, right, is 0.246, and of course this is 0.246. I mean, this is really good, and I think we would get closer if we did more trials. I don't want to do more trials. It'll, you know, it'll run a bit slow on here, but yeah. So notice we can take a sampling approach to arrive at this closed form. And I've been doing this the last few days with kind of, I don't know, fairly obtuse distributions, you know, generated by functions that I invent on the spot. And that's okay, you know, like, there are a lot of things out in the world that don't follow distributions we would expect, and we want some sort of approach to being able to analyze them. So yeah, this is there's kind of a lot of code here. I think I'm often putting a lot of code into the Slack, but I think there's a lot here that you could go through and you know, gain some comfort with, gain some understanding through it. You know, you definitely want to be able to translate mathematical language into functions. You definitely want to be able to do that, right? We're seeing that here with factorial combinations, binomial PMF. And you want to be able to understand CDFs in general, like we did with Poisson, or as we're doing here with binomial. And you want to be able to answer questions like, what is the probability of getting 3 or less successes in 9 trials? Well, we have this closed form of the binomial CDF. We can just use that. That's pretty easy. If you go back to, I think it was the last study hall, I think that's where I get into some stuff with rolling dice, possibly. I mean, I'll probably just do another video where we're exploring some less you know, documented random process. Like, these are very well documented random processes, like flipping coins. We might explore something that's a little bit yeah, a little more esoteric, like even if it's rolling dice, you know, we can take a similar approach to rolling dice. We don't have the closed form necessarily, but we can actually build a reasonable function. We can estimate a function we can estimate a PMF function using machine learning. And that's probably not something I'm going to do in the study halls, but it's something that if you can build a set of samples and have that sample space, and you have some process that generates a random variable, you basically have inputs, right? You have inputs and you have outputs. You can train a machine learning algorithm on that and have that, give you potentially a function that is understandable depending on the random process you're using or the underlying phenomenon. That's not always going to be true. Often that's not going to be true. When people talk about black boxes in machine learning, often they're not saying that you can't look into the findings of the machine learning algorithm. Kind of what they're saying is you're not going to find a nice way to write that as a mathematical formula. And that's just how it is. Often, like with neural nets, you end up with these you end up with these trained arrays of weights, and you have some kind of function that is incredibly complex but does a reasonable job, and you have some level of uncertainty kind of worked into that. It's pretty hard to represent uncertainty in sort of a convenient mathematical function. So we can do that here, right? We can do that with the Binomial Pmf and the Poisson Pmf. But we can also, if we don't have those means, if we don't have those kinds of mathematical formulas, we can take sampling approaches, and you might experiment with different phenomena, like instead of generating bits, you might generate a dice roll, right? That's something that I did recently in one of these study halls, and kind of went down that rabbit hole for a bit. Yeah, so it's Friday. I don't see a lot of questions coming in, and I think I'm going to call it for the day. This is a good stopping point. Next time, I'll probably spend some time on the geometric distribution, and then in subsequent study halls, I'll continue to do more of these kind of dictionary manipulation kinds of things. Maybe I'll try to one-off derivation of Poisson from binomial in, if not a lot of people are asking questions, and maybe I'll do that before I record something a little more formal. But yeah, thanks for watching, and have a great weekend. If you get stuck on stuff, post in the channel. I think a lot of people are studying right now for the technical interview. And if you have questions about the technical interview, reach out to me, reach out to Clark Walker, and we'll do our best to answer. The technical interview cutoff is coming up really soon, so you want to try to interview in the next couple weeks to get into the DSI for October. Yeah, we're going to be a little bit swamped, but please reach out. We'll do our best to get back to you. Please don't get mad at us if we don't get back to you as quickly as we would like to. But yeah, thanks so much, and I'll see you all soon.